Here's something that might surprise you. When ChatGPT reads the word king, it doesn't see letters, it doesn't see a word, it sees a list of numbers. Maybe 768 of them, and the relationship between those numbers encodes the meaning of that word mathematically. How mathematically? Like this. Take the numbers for king, subtract the numbers for man, and the numbers for woman. The result, the numbers for queen. The model learned that on its own, just by reading text. That list of numbers has a name. It's called a vector. And once you understand vectors, really understand them, you start seeing the same pattern everywhere. In search engines, in image recognition, in every recommendation you have ever received from Spotify or Netflix. That's what this video is about. Hi, I'm Bishir. This is video 2 in the complete free series of all the math you need for AI and machine learning. In the last video, we got the big picture of linear algebra, and now we go deep on the single most fundamental idea in all of machine learning. Let's go. Before any equation, I want you to have two separate mental pictures of a vector. Both are true, both are useful, they're the same object seen from different angles. Mental picture 1. A vector is a description. Imagine you are telling someone about your morning coffee. You could say, it's hot, it's strong, it's sweet, medium size. Now, instead of words, use numbers. Hotness, 8 out of 10. Strength, 9 out of 10. Sweetness, 3. Size, 6. So your coffee is 8936. That list of numbers, that's a vector. That's genuinely it. A vector is a list of numbers that describes something. The numbers are called components. The thing they describe can be anything: a coffee, a house, a person's preferences, a word, an image, or any other thing that can be quantified. Now, here's why this matters for AI. Your model cannot read the word cat. It cannot look at a photo. It cannot understand this customer is unhappy. Everything has to become numbers before a model can touch it. The first job of any AI system is to turn the world into vectors, and then all the math happens on those vectors. I want to give you a second mental picture of a vector, because this one is going to stick with you. Imagine a flat grid, like graph paper. You're standing at the center, the point 0, 0, and I tell you, move 3 steps to the right and 4 steps up. So you do, and now you're standing at the point 3, 4. If you draw a line from where you started to where you ended up, that's an arrow, and that arrow is a vector. It has two things: a direction, which is the way it points, and a length, which is how far it goes. Now here's the connection that makes everything click. The arrow pointing to 3, 4 on the grid. It is the list 3, 4. The picture and the numbers are the exact same object, just described two different ways. One is geometric and the other is algebraic, but they are the same vector. Alright, let's get into the formal math. First, notation. When you see V equals V1, V2, V3, those subscripts are just labels. V1 means the first component, V2 means the second, V3 means the third. You'll also sometimes see a vector written with a little t at the end. Transpose. The t just means write it as a vertical column instead of a horizontal row. The math is completely identical either way. It becomes relevant in the next video, and we've already discussed it in the first video in this series. Operation 1. Addition. To add two vectors, add the matching positions. First component with the first component, second component with the second, the third with the third. One rule you cannot break both vectors have to have the same number of components. You cannot add a list of 3 numbers to a list of 5. Operation 2. Scalar multiplication. A scalar is just a plain single number, not a vector, just one value. A single number, nothing else. When you multiply a vector by a scalar, you multiply every component by that number. The effect is simple. The arrow stretches or shrinks, but the direction is always preserved, or exactly reversed. It never rotates. Only the scale changes, which is exactly why we call that number a scalar. Operation 3. And this is the biggest one, the dot product. The dot product takes 2 vectors and collapses them into a single number. Let's run through it with real numbers. Suppose A is 1, 2, 3, B is 4, 0, negative 1. 1 times 4 is 4. 2 times 0 is 0. 3 times negative 1 is negative 3. Add them all together. 4 plus 0 plus negative 3 equals 1. So the dot product is 1. Now, the calculation is simple, but what does that number actually mean? The dot product measures how similar 2 vectors are in direction. If 2 vectors point in nearly the same direction, the dot product is a large positive number. If they are perpendicular, completely unrelated, the dot product is 0. And if they are opposite directions, it's a negative number. There's a formula underneath that makes this precise. A dot B equals the magnitude of A times the magnitude of B times the cosine of the angles between them. 0 degrees gives cosine of 1. 90 degrees gives cosine 0. 180 gives negative 1. It's answering the question, how similar are these 2 vectors? And that question, how similar are these 2 vectors, turns out to be one of the most important questions in all of machine learning. Operation 4. Magnitude. The magnitude of a vector is its length. How far the arrow reaches. You calculate it by squaring every component, adding them up, and taking the square roots. For the vector 3, 4, 3 squared is 9, 4 squared is 16. Add them to get 25. Square root of 25 is 5, so the length is 5. This is just the Pythagorean theorem extended to any number of dimensions. The dot product is affected by both direction and size. If you stretch a vector to be twice as long, its dot product with anything else doubles, even if the direction hasn't changed. So if you want to measure only similarity, only direction, you need to cancel out the size. That's what cosine similarity does. It takes the dot product and divide by the magnitude of both vectors. The result lands between -1 and +1. -1 is exactly opposite directions. 0 is completely unrelated. +1 is identical direction, regardless of how long either vector is. This one formula is what powers Google search, Spotify recommendations, and Word embeddings. Let's build it in code. Let's implement everything by hand first, because once you've written it manually, you actually understand what the library is doing. Starting with addition, we loop through each index and add the matching components. Run it, we get 5, 2, 2. Scalar multiplication. We multiply every element in A by 2. That gives us 2, 4, 6. Exactly how we calculated it earlier in the board. Now the dot product. We multiply the elements at each position together and sum them up. So A0 times B0 plus A1 times B1 plus A2 times B2. Run it, we get 1. For magnitude, we square each component with the double star operator. Sum them all and wrap it in a square root. For vector A, that comes out to about 3.74. For vector B, about 4.12. And finally, cosine similarity. We take the dot product, which is 1, and divide both magnitudes multiplied together. 3.74 times 4.12 gives us roughly 15.4. So 1 divided by 15.4 is about 0.065. That score is close to 0, which tells us that these two vectors don't point in very similar directions. Now let's redo all of that with NumPy. We import NumPy as NP and convert our Python lists into NumPy arrays with np.array. Addition is literally A plus B. One operator, same result. Scalar multiplication is 2 times A, same thing. For the dot product, there are 2 styles you'll see in real machine learning code. NP dot of A and B is the classic approach. The @ operator is the modern style. You'll see it constantly in PyTorch and TensorFlow. Both produce 1. Magnitude is np.linalg.norm, NumPy's full linear algebra toolkit in one submodule. Cosine similarity is just np dot divided by the product of both norms. One clean line, same 0.065 we computed manually. Everything checks out. Now let me show you 2 quick sanity checks that confirm the formula is actually working the way we said it would. Perfect similarity first. I'll keep A as 1, 2, 3 and define C as 2, 4, 6, which is just A stretched by a factor of 2. Same direction, twice the length. Run cosine similarity on them and we get exactly 1.0 maximum score, because direction is identical regardless of the difference in size. That's exactly the behavior we wanted. Length doesn't affect the similarity score. 0 similarity next. A is 1, 0 and D is 0, 1. The horizontal and vertical axis. They're perfectly perpendicular. Cosine similarity gives us 0, 0, completely unrelated directions. 0 score. The math is doing precisely what the geometry told us it would. Here's where this stops being math and starts being magic. Your data is made of vectors. Every row in a dataset is a vector. A house described by bedrooms, bathrooms, square footage, distance to the city center, 3 to 1400, 5. That's a vector in 4 dimensions. Your dataset of 10,000 houses is 10,000 of those vectors. Your model learns by computing dot products on them. Let's make this concrete with something more grounded. Say you're building a property recommendation system. Each house gets described by 4 numbers: bedrooms, bathrooms, square footage, and distance from the city in miles. That's a vector with 4 components, 1 per feature. House A, 3 bedrooms, 2 bathrooms, 1400 square feet, 5 miles out. House B, nearly identical to A. House C, totally different property. I'll write a quick cosine similarity function. It is just the dot product divided by the product of the norms, same as before. Now I'll run it pairwise. A against B scores 0.9996. 2 nearly identical vectors, nearly identical score. A against C is noticeably lower. The math picked up that A and C are quite different. Now, here's what's interesting. You could have looked at those numbers and seen that yourself. The point is that this function will do the same comparison across a catalog of million properties instantly without you looking at any of them. Same calculation, massive scale. Images are vectors. A 28 by 28 pixel black and white image has 784 pixels. Each pixel has a brightness between 0 and 255. Stretch it out flat, It's a list of 784 numbers, a vector in 784 dimensions. Your model never sees the digit 7, it sees a 784-dimensional vector and learns to classify it.
Here's a 4x4 grayscale image laid out as a grid of numbers. Each value is a pixel brightness between 0 and 255. 0 is black, 255 is pure white. Everything in between is some shade of gray. The whole image is just numbers in a grid. Now watch, we call dot flatten on it. That one method call collapses the 4x4 grid into a single, flat list of 16 numbers. The shape goes from 4x4 down to just 16. And that flat list, that vector, is what your neural network actually receives as its input. The model never sees a picture. It sees 16 numbers. It never knows where the rows and columns are.
Language is vectors. This is the one that stops people cold. When a language model processes the word king, it doesn't see letters. It looks up a vector, maybe 768 numbers, that encodes the meaning of that word as a point in high-dimensional space. And here's the result that shook the field. Take the vector for king and subtract the vector for man and the vector for woman. The closest vector in the entire vocabulary is queen. The model learned that relationship on its own, just from reading text. Vector arithmetic captured meaning. The direction from man to woman is the same direction as from king to queen. Gender is a direction in vector space. That's the dot product doing exactly what we described, measuring similarity, capturing direction, encoding relationships as geometry.
Let's define our 4 vectors as king, man, woman, and queen. In production, this would be 768 numbers or more that encodes the meaning of the word as a specific location in a very high dimensional space. I've reduced the vectors to just 4 dimensions here, just so the code stays readable. The principle holds at any dimension. Now we do the arithmetic. Result equals king minus man plus woman. What we are doing is starting with the meaning of king, subtracting out the male association, and adding the female association. And we want to see where in the vector space we end up. Let's measure cosine similarity between result and queen, and also between result and king for comparison. Result versus queen comes out close to 1.0. They are pointing in nearly the same direction. Now result versus king is noticeably lower. We moved away from king when we did the subtraction and addition. The model was never told what gender is. It was never told that king and queen are related. It figured all of this out just by reading enough text and noticing that the direction from man to woman keeps showing up in the same relationship as the direction from king to queen. Gender became a direction in the space. That's the dot product detecting geometric structure in meaning at scale. Last one, and this brings everything together. When you type a search query, that query gets converted into a vector. Every page in Google's index has a vector. Google's job is to find the pages whose vectors point most closely in the same direction as your query. Highest cosine similarity gets shown first. Here's the simplest possible version of that system. A query vector, a relevant document, and an irrelevant one. We compute cosine similarity between the query and each document. Document A, the relevant one, comes back with a high score. Document B, the irrelevant one, scores low. So A surfaces first. That's Google search reduced to its core idea. In reality, they are running this against hundreds of billions of documents, billions of times a day, with a lot of very clever engineering layered on top. But the operation at the center of it all is exactly what you just built.
A vector is a list of numbers that describes something, and you can also picture it as an arrow in space. Both views are the same object. You can add vectors, Stretch them with a scalar and measure the dot product between them. The dot product gives you a similarity score. How much are these two things pointing in the same direction? Cosine similarity normalizes that into a clean -1 to +1 range. And that idea, similarity between vectors, is the engine behind search engines, recommendation systems, word embeddings, image recognition, and every AI system you use every day. In the next video, we take a collection of vectors, organize them into a matrix. Your entire dataset is a matrix. Neural network weights are matrices, and the single operations that run every forward pass in every neural network ever built is a matrix multiplication. If this helped you, don't forget to like and subscribe. The full series is free and we are posting every day. Drop a comment with the thing that surprised you the most about vectors. Or if you have any questions, I read and reply to all of them down in the comment section. I'm Bishir Tijjani. See you in the next video.